Okay, hi everybody. We'll get started. I'm Tom Griffiths. I'm your interdisciplinary flavor for today. As you see, you'll get two disciplines for the price of one. I am in a department of psychology, but also a department of computer science. So I'm going to give two talks, one today and one tomorrow, that are both about how the intersection of psychology and computer science can, do some useful things for us in the context of understanding aspects of human decision making. So the talk I'm going to give today is about the rational use of cognitive resources. So this is basically using computer science to give us models of decision making, and I'll explain more about what that means in a moment. The talk I'm going to give tomorrow, the title it's on the program is slightly wrong. So the talk I'm going to give is Evaluating Models of Decision Making with Large-Scale Online Experiments. The title that's on the program is Evolutionary Models of Decision Making with Large-Scale Online Experiments. They're a little bit different. Interestingly enough, if I have time, I'm actually going to present an evolutionary experiment in the talk tomorrow, so it wasn't that wrong, but it's a little bit wrong, but I wanted to make sure no one's disappointed when we get there tomorrow. So the talk today is really motivated by the different views of the mind that I get as somebody who's in these two departments of psychology and computer science. So you as economists have another perspective on human minds, but the perspective that I get as a psychologist is mostly that humans are kind of embarrassing, right? So if you walk into a psychology department, you ask about human beings and how good they are at doing things like making decisions, you're going to get a lot of sort of like pessimistic answers. There are books that have titles like Predictably Irrational, Inevitable Illusions, How Mistakes of Reason Rule Our Minds, How We Know What Isn't So, The Fallibility of Human Reason in Everyday Life, or Cluj, The Haphazard Construction of the Human Mind. And the theme of all of these books is that we're not great at doing the things we're supposed to be doing, at least as evaluated against the kind of standard models that you as economists are very familiar with. There's various ways in which we behave irrationally. There are simple heuristics that we follow that result in systematic biases. It's not a great picture of human cognition. On the other hand, when I walk across the campus to the computer science department, I find out that humans are inspiring, right? So the history of artificial intelligence research is one of trying to make machines that are able to do the amazing things that human beings are able to do. And so if you're an AI researcher, often what you're trying to do is, take some amazing capacity that human beings have, build a machine which is able to do that, and for, despite all of the progress in artificial intelligence in the last couple of decades, there are still all sorts of things that human beings can do that we're still not able to make machines do. So this is a classic example of AI researchers being inspired by human cognition. So this is Garry Kasparov playing against Deep Blue. Kasparov lost this match ultimately, but that doesn't mean that we can't still be inspired by what the human being is doing in this picture, right? So even though the computer ended up winning, it's worth pointing out it wasn't entirely a fair match, right? So there's a significant difference in the kind of processing speed of these two different systems. Right, so Kasparov's evaluating on the order of 1 position per second, maybe up to 10. On the other hand, the computer is evaluating on the order of about 100,000 positions per second. Right, so it's sort of able to search a much wider range of possibilities. The system on the right here is powered by an industrial power plant. The system on the left is powered by black coffee and a piece of toast. Right, there's sort of like a massive difference in the efficiency of these two systems. And so what this tells us is that there's still all sorts of inspiring things about human cognition for us to discover, in particular how it is that we're able to use the computational resources that we have efficiently to allow us to do all of the amazing things that we're able to do. So what I'm going to try and talk about today is how I can think about resolving that paradox, right? How it is that we're, on the one hand, able to be inspiring in terms of the things that we can do. On the other hand, act in ways that I think are unambiguously not consistent with the kind of standard conceptions we have of rational behavior. And basically the resolution I'm going to argue for comes down to two things. One is that we have limited cognitive resources, right? That's something that leads us to make errors in decision making. This isn't a controversial point. This is sort of the idea of bounded rationality goes all the way back to Herbert Simon in the 1950s. And has been carried forward through various disciplines since then. But the other is, I think, a more novel premise, which is that we do a good job of using those resources. And that's something which lets us solve many different kinds of problems efficiently. And so what I'm going to focus on in the talk today is trying to really lay out what it means to do a good job of using our cognitive resources. and then explore how well that can help us understand some of these things that people do that are on the face embarrassing to us. So in order to do that, the first step is really to rethink the way that we think about rational action. And so I think for most of the people in this room, when we talk about rational behavior, we have something in mind along these lines, right? It's expected utility, take the action that has highest expected utility. We think about this as an optimization problem. That optimization problem is expressed in a way where we're optimizing over actions. We want to maximize the expected utility associated with those actions. We can reduce this to a slogan. The slogan is something like do the right thing, where the emphasis is on the thing, the action that we're doing. That's the way that we're going to evaluate someone's rationality, is by the actions that they choose with respect to this kind of criterion. But there are a few ways in which this doesn't work for us as a theory of rational action. And then, again, us can be computer scientists or psychologists. So one way that it doesn't work for us as computer scientists is that it doesn't take into account how hard you have to think in order to figure out what the right thing to do is, right? So if you're a computer scientist, you're obsessed with not just taking actions that make sense, but not spending forever trying to figure out which action is the action that you should be taking. There's a trade-off between the quality of the actions you take and the amount of time that goes into that computation. And that trade-off is not reflected in this way of characterizing rational action. And so for that reason, when people in artificial intelligence were trying to think about, how do you design a sort of criterion of rational action that works for a robot, this kind of criterion is not one that's effective because it doesn't take into account that trade-off. One way that it's unsatisfying for us, in this case, I guess me as a psychologist, is that it doesn't say anything about what goes on inside your head, right? So as I said, the emphasis here is placed on the actions we take in the external world, and it doesn't say anything about the cognitive processes that you engage in order to select those actions. And that's related to the computer scientist's problem, right? The computer scientist says, you haven't said anything about how hard I had to work in order to get this solution. The cognitive psychologist says, you haven't said anything about what I had to think about in order to make this choice. And so we can solve both of those problems by using a different kind of criterion for evaluating rationality. I'm going to call this criterion resource rationality. I'll say in a moment how it relates to other things that you've been hearing about the last couple of weeks. But here the idea is to move the emphasis from that external action and instead put it on the strategies that we use in order to select those actions. So here the way that we're going to characterize a rational agent is the one who is making the best use of their internal resources in order to achieve whatever it is that they're able to achieve in the world. And so the way that this is formalized here is to say we want to focus on using the strategy that best trades off utility and computational cost. So now our optimization, our sort of outer loop here, is over strategies or policies or algorithms, pi. And then in the inner loop, we have these two terms, right? So one term, the one on the right here, is the cost that's associated in executing a sequence of computations that give us a sequence of beliefs that then, when we end up taking our action based on those beliefs, lead us to take a reasonable action at the end of the day. And so the way that this is expressed is now precisely in terms of this trade-off between how hard we have to think and what the quality of the outcome of that thinking process is like, where we're making the assumption that you sort of take the best action based on the beliefs that you're able to get to as a consequence of thinking about what you should be doing. And so here, the way that we're evaluating our agents is in terms of how well they're sort of like how good the algorithms are that they're using for solving this problem, rather than focusing purely on the external actions.
Is this choosing strategy seems like a more complicated problem than choosing the action?
Yep.
So there's going to be a cost associated with that
Yep.
as well?
Yeah, and so I can talk more about, there are sort of versions of this where you can get into that. But for now, what I'd say, right, so the concern is I've now moved us up a level of abstraction, right? I've moved us from what people in this literature call the object level, which was the original decision problem, to the meta level, which is now the level at which we're trying to decide what strategy to use to solve that decision problem. Optimizing over strategies is potentially a more complex thing to do than optimizing over the original decision problem. But having moved up that level of abstraction, we've also changed things like the time scale that we're operating over and the sources of data that we can use in that optimization, right? So if you think about individual decisions as operating at a time scale of seconds or something like that, strategies we can learn over the course of a lifetime, right? So we've opened ourselves up to more opportunities to solve that optimization problem. Okay. So if I kind of reduce this to a cartoon, it might look something like this, right? Expected utility theory, we're not talking about what's inside people's heads, we're just talking about the actions that we take. Resource rationality, we've moved the emphasis off the external world and put it on the internal one, and we're going to talk about the sequences of computations that are going on inside people's heads in order to end up choosing the right action. And so this addresses my two concerns as a computer scientist and as a psychologist. We now have a way of talking about the computational cost that's involved in solving a problem. And we also have a way of saying something about what people should be thinking about in the context of solving a particular decision problem they're trying to solve. So I wanted to take a moment and try and relate these ideas to things that you might have heard about before, right? So in the economics literature, there's literature on rational inattention. And then a lot of the models that I'm going to present draw from this tradition of what's called bounded optimality in the artificial intelligence literature. And so both of these kinds of theories are about how do we make the best use of a limited resource, right? So in rational inattention, that resource is something like the investment that we can make in order to improve the quality of the signals that we're getting. In bounded optimality, that resource is the computational cost that's involved in executing a sequence of computations. And so I think about these two ways of formulating these resource trade-offs as maybe corresponding in some ways to different aspects of the psychological problem here, where the inattention case is a little more like the psychological problem of perception. You're just trying to make sense of signals that are provided to you from the world under the constraints that you have about the resources you have for processing those signals. Whereas in the bounded optimality models that I'm going to present, the focus is more on something which is closer to the cognitive processes that we're going to engage in order to gather information and make decisions based on the information that we've obtained. And so in this talk, I'm actually going to talk about problems that I think are actually things where you can start to sort of have a bit of a continuum that connects these different traditions. So one source of connection is by thinking about things like sampling from the world, just generating random samples. That's a discrete process I'm going to model discretely, but it has nice connections to this sort of information theoretic view of perception. Another connection is through representation. You've heard from Mike about some of the ideas about efficient coding. If I have time today, I'll talk a little bit about some work from my lab on resource rational representation that gives us a way of thinking about how representation might work within this more cognitive framework. But in general, I'm going to talk about the sort of broader framework of thinking about the trade-off between the computational resources we use and the quality of the decisions that we end up with in terms of resource rationality. So that's the term I'm going to use for talking about this kind of framework. So any questions before I dive in? Okay. So one thing that you can do now that we've given ourselves a different definition of maybe what rational action might look like is to go back and look at some of those things that were on my list of things that we do that are sort of embarrassing and ask, well, actually, can we make sense of those? Can we sort of put them back into the inspiring column, right, as like sensible uses of the limited computational resources that we have? And so some of the early work that we did in this tradition was really taking classic kinds of heuristics and going and asking, okay, is there a way to interpret these sorts of heuristics as things that make sense in terms of use of limited computational resources? And so I'm just going to focus on two of these cases. I'm going to go through them relatively quickly just to give you a sense of what it means to sort of like look at some of these heuristics and maybe how they could be explained within this framework of resource rationality. And this first part of the work is all joint work with Falk Leader. So one classic heuristic is the anchoring and adjustment heuristic. We can do this as an audience participation moment. I'm going to ask you a couple of questions. I'd like you to write down or think about what your answer to those questions might be, and then we can see if this works as an experiment. Okay, so is everybody ready? Okay. So first question, what is the freezing point of vodka? I actually have answers in both Fahrenheit and Celsius, so you can choose. Okay, and second question, how long is Mars's orbit around the sun expressed in Earth days? Okay, everyone's got their answers. All right, So the correct answer for the freezing point of vodka is minus 17 degrees Fahrenheit or 27 degrees Celsius. It actually depends on the proof of the vodka, but I'm just going to use one of those numbers. Okay, so if the number that you came up with was higher than that number, so it's like a warmer temperature, can you raise your hand? Okay, and then a lower temperature. Interesting. Okay, and the length of Mars's orbit around the sun is 687 days. So if you had a smaller number, large number, yeah. So one of those worked, I think. So the idea is that when people have these kinds of questions, they answer those questions by starting with a more familiar example, right, an anchor, and then adjusting away from it, leading to bias, right? And so for the questions that I asked you, the obvious anchors are the freezing point of water and the length of Earth's orbit around the sun, right? And so the idea is you start with something like the length of Earth's orbit, and then you adjust away from it, but then you don't adjust sufficiently to get to the point where you end up getting to the right answer. And so that's sort of the phenomenon of anchoring and adjustment. But what we were interested in was, are there circumstances under which we can understand this as a reasonable strategy? In particular, can we understand the inadequate adjustment away from the anchor as something that makes sense? And so to formulate this as a problem, we can think about, what we're trying to do here is estimate a quantity based on some sort of uncertain cues that we get from memory. We have to assume some sort of architecture that's going to tell us what sorts of computations are available to us. I'm going to talk about this in the context of thinking about it as a Markup chain Monte Carlo algorithm for estimating this quantity. So we're trying to sample from our posterior distribution via this iterative algorithm. In fact, there's a lot of other choices we can make about this architecture. Things like gradient descent methods, a variety of iterative algorithms. I'll talk about what the criterion is for what architectures this applies to when I get to the results. And then we're just going to assume that cost is something that increases linearly in the number of samples that we generate, right? So it's just like an opportunity cost. And so for people who haven't seen this before, the Markup chain Monte Carlo algorithm, called the Metropolis Hastings algorithm, the way that it works, you start out with some initial estimate of a quantity, and then you have a proposal distribution, that's the little Gaussian distribution down there. As you, let's see if this works. Yeah, okay. So you have a little Gaussian distribution. You propose a variation on your starting value, and then you have in mind, you're sort of able to measure at points the true target distribution. So you say, well, is this proposed value higher in probability under the target distribution than my current value? If the answer is yes, then you accept it. If the answer is no, then you might still accept it, but you gradually refine your estimate, and then over time you can show that regardless of where you start out, you converge to something which is now a Markup chain that is, the stationary distribution of this Markup chain corresponds to the distribution that you're trying to sample from. So over time, you converge to something which is like samples from that distribution. And so here this histogram is constructed just by collapsing the last half of my Markup chains here. And you can see it does a pretty good job of approximating the true distribution. So the way that we formulate our question then is, how many iterations should you run your Markup chain Monte Carlo algorithm? Right? So if the cost of running the algorithm increases, the longer you run the algorithm, is there a reason to stop running it before you converge to that target distribution? And so what you can show is that under a very simple model, producing a biased estimate is resource rational. And this model is based on the fact that this kind of algorithm, the bias in that algorithm is something that decays exponentially. So this is the number of iterations that you run your sampling procedure. And this is different starting points you can start out at. So these different lines correspond to different numbers of standard deviations away from the mean of the prior distribution. Regardless of where you're starting out, you get this exponential convergence towards, of the mean of the samples towards the mean of the distribution. And so this is a property of MCMC algorithms. The results I'm going to talk about apply to any other algorithm that converges geometrically, right? So that includes things like, as I said before, gradient descent algorithms, a bunch of other iterative estimation procedures. But the basic idea is that if bias is decaying exponentially and cost is increasing linearly, then you're going to hit a point where it makes sense to stop sampling because the marginal return for additional sampling is so small that it's fallen below the linear cost for drawing an additional sample. Yeah.
Can you say more clearly what's the problem there? I mean, is this related to trying to figure out how much it takes mass to orbit around the sun?
Yeah. So the idea is.
What's the procedure there?
So the idea is that this kind of, so you have some fuzzy,
Yeah.
things in your head from which you construct a posterior distribution, right? You don't have access to that full posterior distribution, but you can answer a question like, is this number closer to the right number?
No, I mean, I stop
Yeah.
right away. I mean, I know that Mars is, is more distant than Earth from Sun, so
Right.
it probably orbits more than Earth.
Yep.
And that's about where I can get.
Yep.
But I don't start sampling anything else.
But so, yeah.
So what are you, can you say more, like, what are you sampling from it? Like, what's, yeah, I'm very confused.
So the quantity here would be that number, right? Like whatever the estimate is you're trying to produce, right? And then this is the posterior distribution that you can construct based on the limited information that you have. So like you have that fuzzy sense of whether one number is a better number or not. And then I've just defined an iterative procedure, which if you run that iterative procedure for long enough, it'll converge to the correct answer.
How?
Oh,
I don't have the correct
yeah.
answer.
Yeah,
How is how am I gonna
converge
convert?
So it'll
orbit around Sun.
No, it'll converge to the samples from your posterior distribution, right, based on the estimate that you're able to construct.
Okay, but my posterior distribution can be very wrong.
Yeah.
So where is, how does this explain that the people are off with respect to the true?
So the idea here is then the point at which you're starting is your anchoring point, right? And so if you started, so let's say we started you with a different high, if the number that you started out with was higher, right? Then the prediction is that you would be biased in an upwards direction rather than in a downwards direction, right?
You're not trying to explain if you're right or wrong, you're trying to explain
The
how
direction of
anchor
error,
affects
yeah.
the,
Yeah, so that you can think about this as, here's the case where you start with, a low anchor, here's the case where you start with a high anchor, then what we want to explain is why it is that you end up with an estimate which is, high on this side and low on this side. So it's inadequate adjustment away from that initial anchor. Yeah.
And how do you select anchors? Is there some similarity to the first signal you have?
Yeah, so for the experiment that I talked about, the anchor is something that, is an intuitive estimate that you have.
Yeah.
That's something that's similar, right? So we don't deal with the question of how anchors are selected in this paper. We just talk about what are the circumstances under which inadequate adjustment makes sense. Right. You guys okay?
No, but I think we're hopeless.
Okay. All right. But the basic idea then is that, yeah.
This dynamics, it's a situation where you get some sort of new information about the world.
No, there's nothing. So in this model,
At least
this
your
is
thinking produces something new at each stage.
no. All you have is this evaluation function, right? That's just telling you is the answer that I've gotten pretty good, right? So you can think about this as the assumption here is that the signal you have access to is one that tells you whether an answer is better or worse. And so what happens as you're sort of like iterating, you're like, oh, that's okay, maybe that's a pretty good answer, right? And so you can make those kinds of comparisons. But there's no extra information that you're getting other than being able to say, an answer I just came up with is better than the last answer I had. Okay, so
I have a question about the next slide.
Yeah.
So the fact that it pays exponentially, it could occur at any rate. If there's a fixed cost, you're going to stop it at some point. So what is so special about the exponential rate?
so all that we need is that this is happening at a rate which is crossing the linear threshold, right? So if you were getting linear decrease in bias for linear cost, then you would run it to asymptote, right? And so we just need that there's a point where we have this crossing over. Yeah. And so that's basically what this is showing. This is showing the crossing over point as a function of starting point, right? So you sort of get that as we vary the cost of doing additional computation versus the cost of errors, that's what's going to determine how much you should sample, right? And so this just makes a very straightforward prediction that the magnitude of the bias that you're going to see is going to be a function of these things: iteration cost, error cost, and then how far away you start from how far away your anchor is from the mean of the target distribution. And so we can just use that very simple model to actually explain some of the phenomena that you see for anchoring and adjustment. So this is, for example, the problems that we looked at, the freezing point of vodka, Mars's orbit around the sun. Epley and Gilovich ran a bunch of these experiments where they actually measured how much people adjusted towards the correct answer. And this varies across problems, but we can actually predict that variation across problems where all that we're doing is we actually go in and we ask people, we measure what people's distributions are for these quantities, and then we can measure how far away their initial anchor is from that value. We have information about what the means and the standard deviations are for those quantities, and from that we can derive a prediction about how much adjustment people would do using that simple model I talked about. Yeah.
The bias depends on decision time?
Yeah. But that same kind of model also predicts a bunch of other kinds of things, right? So for example, because you care about this trade-off between iteration cost and error cost, things like cognitive load, time pressure, and alcohol, all of which increase iteration cost, are things that are going to reduce the amount of adjustment that people do. Giving people stronger incentives, that's giving people a greater error cost, can increase the amount of adjustment people do. As the anchors become more extreme, you get a greater bias. That's something that falls out of the model that I talked about. If you're more uncertain, that distribution is more variable, then you're going to get more anchoring because you're not being pulled towards that distribution in the same way. And having more knowledge, which means like making that distribution tighter, can reduce the anchoring bias, and so those are all consistent with that simple model that I was showing. Okay, so this is just, again, intended as an example to show you kind of like what it might mean to explain a heuristic using this kind of trade-off between computation and error. Questions about this? Okay, so let me do a second example. So, so this example is the availability of extreme events, right? So the availability bias is another of these sort of well-known biases. People overestimate the probability of events that come to mind easily. Extreme events are things that come to mind easily. So, you have a question?
Yeah, actually, about the previous one. So that doesn't really say how people actually engage in the computation. All it says is they will lie on this optimal curve.
Yeah, yeah. It's not intended as a claim about specific cognitive mechanisms. It's just saying, assuming those mechanisms have a decay, you know, with iteration in the way that I was showing, then we would expect this to happen. So, you know, extreme events are things that come to mind easily, right? If you're going to think about going snorkeling, you should be thinking about something like this. You're probably thinking about something like this, right? So this is a low probability extreme outcome, and you know, the literature tells us that people tend to overestimate the probability of those extreme events. And so the question is, why would that be? Well, again, we can sort of think about this as a problem where we have limited computational resources that we're trying to use to estimate a quantity. So in this case, if we're trying to decide what action to take, we want to estimate the expected utility of that action. This can be something that's quite a complex computation, as it requires integrating over all of the possible outcomes, the probability of that outcome times the utility associated with that outcome. And so what we're going to do is, instead of integrating over all possible outcomes, we're going to generate some samples from some distribution of the possible outcomes of the action. And those, we're going to assume that at the end of the day, we're going to combine those samples together, maybe with some weights on those samples, and that's going to be the way that we're going to estimate our expected utility. And again, we're going to assume that cost increases linearly in the number of samples. So really what we wanted to be able to do is to come up with a way of estimating that utility while not generating a lot of samples, right? So we want to find good ways of estimating expected utilities from small numbers of samples. So the intuitive response when I talk about sampling is that maybe you should do some, you know, simple Monte Carlo, right? We have an expectation of a utility with respect to probability distribution P. You could just generate samples from that probability distribution P, and that gives you an unbiased estimate of the expected utility. There's only one problem with that, which is that with small numbers of samples and skewed distributions, that's something which can result in bad outcomes, right? So if you have a distribution where there are rare events that have extreme utility values, if you're just generating a small number of samples using simple Monte Carlo, even though that estimator is unbiased, it has extremely high variance. And in this case, it's the variance that kills you, right? So what we want to do is then find an estimator that is not subject to the same kinds of concerns about variance. And one of the ways that computer scientists reduce the variance of a sampling estimator is by doing something called importance sampling. So the way that importance sampling works, we have probability distribution that we want to sample from. So this is our true probability distribution P. But instead of sampling from that distribution, we sample from another distribution, Q. And then to correct for the fact that we sampled from the wrong distribution, we then take the samples that we get and we assign those samples weights, where those weights are proportional to the ratio of P to Q. And so here the idea is that for points that we've sampled from Q, but that have low probability under P, we want to downweight those samples. And so that's going to happen because Q is large and P is small. So we assign small weights to those samples. And then for points that we've sampled that should have high probability under P, that have lower probability under Q, we're going to upweight those samples. And that's going to happen because here P is greater than Q. And so this gives us a way of correcting for the fact that we've sampled from the wrong distribution. And so then we can calculate our expected utility by taking an average across these weighted samples that we've generated. And so now this gives us an extra degree of freedom. We want to try and estimate our expected utility. We now have the choice of this probability distribution Q that we're going to generate samples from. And the question is, how should we generate those samples in order to minimize the variance of the estimate that we get so that we can have an estimate that's going to behave well if we have small numbers of samples. And what you can show is that the variance minimizing estimator uses the proposal distribution Q, where the probability that you generate a sample from this distribution is proportional to the true probability, P, times the absolute value of the utility associated with that outcome minus the expected utility. So this is the deviation of the utility from the expected utility that we're trying to evaluate. And so what this says is that if you're going to approximate a probability distribution with a small number of samples for solving this problem of evaluating the expected utility, you actually want to use a set of samples that reflect both the probability and the absolute value of the utility. The resulting estimator minimizes variance, but you're trading off variance for bias. And so with small samples, you overrepresent extreme events, and so your expectation is skewed towards those extreme events. Yeah.
It seems as though you need to know the expected utility to begin with to compute this
Yeah.
rule, which you then use to compute the expected utility. So it's circular.
So this is, it's circular in terms of like the theorem here, right? In terms of like giving a characterization of what the optimal distribution is. If you're an agent who's trying to, make a decision, you can make an assumption like, for example, if you assume that expected utilities are small relative to extreme utilities, then you're pretty safe just using the absolute value of the utility, and that gives you a pretty good approximation to the optimal distribution. Yeah.
And there you're imposing that Q has to be a normal and cannot become bimodal or cannot adapt.
No, Q can take whatever form you get from following this. There's no constraints. It's just proportionality. So you think about it as you have your original distribution P, whatever it was. You have this extra utility function U, right? And then we're going to take the pointwise product of those and renormalize, and that's going to give us our generating distribution. And there's simple psychological mechanisms that can do this. So, for example, if you walk around the world, encounter things of probability P, and store them in memory with probability proportional to U, then you're going to have generated an internal distribution that has that property. Right. So as long as you're more likely to remember more extreme events, then that automatically does this when you're restopping from it. Yeah.
The variance is the payoff variance?
It's the variance in the estimate of the expected utility. Yeah.
Why would you want to remove it?
I didn't show it here, but in the paper we show that that's if you're making decisions from small samples and you have this skewed distribution of utilities, then that's the thing that results in the best small sample decisions. So it's just what I was saying before, which is that if you're so for any estimator, if you're generating an estimate from a small number of samples, variance is a bigger factor than bias in determining whether you actually end up making the correct decision. Because with small numbers of samples, variance is going to be large for any
So the
estimate.
assumption is that I'm just going to follow the sampling distribution. So I have a sample. Is there a presumption that I'm going to take sample distribution.
You're going to take the expectation with respect to the weighted
Exact
sample
one.
distribution, yeah, and then make a decision based on that. Okay. All right. So these are two examples of cases where we can take something which is a known heuristic. Oh yeah.
Can I just clarify, like the sampling, can I think of it as selective memory?
Yeah. Yeah. So that's what I was saying. So a mechanism that induces this kind of distribution is one where if you encounter things in the world with probability p, you store them in memory with probability proportional to absolute value of u, then that means that when you recall those things later, then you're going to be sampling from this distribution. Yeah. Yeah.
So from a rational, from a research rationality perspective, so I imagine two scenarios. The first scenario, basically using this forecast for someone else, I cannot make a decision. Second, I'm going to make my own decision based on this information. Do I know anything about the
I mean, so if you just care about the expected utility under both of those, then the answer would be the same.
But then it typically says people will stop sampling after making a decision. Like, people say you're coming to resources,
Uh-huh.
you make a decision, you shouldn't be sampling anymore.
Yeah.
I thought we have some rational position in this field, like visiting the observation after the decision is done.
Yeah, so I don't have any opinion about that. So, like I think you could propose that whatever mechanisms you use for generating samples are things that you don't have. You have a sort of endogenous sampling mechanism, and you can make a decision when you're done sampling, but maybe it just keeps on running, right? That's plausible. But, yeah. All right. So these are cases where we kind of we could take sort of existing heuristics and sort of say, okay, maybe there's a way that we can think about that in terms of this trade-off between computation and error. But there's also a sense in which these were easy cases because we're giving a post hoc explanation for something that we already knew about, right? So what I'm going to focus on in the rest of the talk is rather than taking strategies that we know people use and then trying to think about circumstances under which they might make sense, how it is that we can go about actually deriving optimal strategies from a formulation of a problem that people have to solve. And so the key idea here is that the way that we've set up this problem of what it means to be a good strategy for solving a decision problem is in terms of the sequence of computations that you're going to execute, right? And so what it means to have a good strategy is that you're able to say, what the sequence of computations you should be executing is based on the information that you're gathering from those computations. And so the key insight here is that this way of formulating what it means to make a good decision means that the choice of cognitive strategy to use when we're solving a problem, the choice of the heuristic that we're going to engage in, is now something that we can reduce to a sequential decision problem. And by sequential decision problem, I mean the sort of canonical kinds of sequential decision problems that we're used to thinking about in the context of decision theory. So our problem of choosing cognitive strategy is now a sequential decision problem where instead of thinking about a sequence of actions we're going to take in the world, we think about a sequence of computations that we're going to execute inside our heads. And what I'm going to now sort of show you is how we can formalize that process using something called meta-level Markup decision processes that we can then solve using methods that come from the literature on reinforcement learning. So can I just get a sense, who's heard of Markup decision processes before? I know this is okay. All right, so some people, so I'll kind of go through and sort of explain what that means. And then I'll show you how we use that to then set up this problem of finding effective cognitive strategies. So the Markup decision process is just a way of describing a sequential decision problem. So here the idea is that we are in some state of the world, and we're going to choose some action that we're going to take, and then based on that action and the current state that we're in, we're going to receive some reward, right? So that's our sort of standard one-step decision problem that we're used to, right? We're going to try and choose an action, and then there's a distribution over rewards that are associated with that. The way that we turn this into a sequential decision problem is to say that the action that you take determines not just the reward that you receive, but also the next state of the world. Okay? So now we have a sequence of decisions where each decision influences the next decision problem that we face. And so the Markup decision process assumes that the sequence of decisions is set up so that each state depends only on the previous state and the action that we took in that state. So this is a Markup assumption. And then that what we're trying to do is then solve this problem sort of unfolding through time, where we care about the cumulative reward that we receive as a consequence of trying to solve that problem. So we don't care about just a single reward, we care about the sum of the rewards out to some finite horizon or out to infinity with some appropriate discounting. Yeah.
Why does the state t affect the reward at t-1?
So I put in these arrows to cover sort of like all formulations of Markup decision processes, but you don't need to use all of those arrows, right? So you can say, my reward depends on the state that I move to, and that's what determines my reward, or you can say, my reward is conditional on the state that I'm in and the action that I take. So there's just different ways of formulating this, where rewards are received based on transitions, right, versus rewards are received based on states and actions. Okay, so the standard formulation of this that's used in like reinforcement learning and machine learning, you might think about state as, you know, you've got a robot which is trying to navigate an environment. The state is the current position of the robot. The actions that are available to the robot are moving in different directions. The rewards reflect a goal that you're trying to get to, right? And so now if I'm a robot and I take a move here, I've changed my state, and now I have another decision problem. I have to decide what move to make next, right? And I keep on moving. And so solving this sequential decision problem is a matter of finding what's called a policy. And what that policy does is it tells you for every state that you're in, what action you should take. Okay? So a policy is a mapping from states to actions. And in doing that, one of the things that you want to compute is the value that's associated with these different states, right? So a quantity that's very useful for you in making your decisions is what's called the Q value, which tells you how valuable it is to take a particular action in a particular state. And you can use that. Basically, the optimal policy is then going to be taking the actions which have the sort of the optimal value, and that value takes into account not just the reward that you receive in the current state, but the rewards that you'll receive pursuing the optimal policy in all of the states that you transition to from that original state. Okay. How are we doing on macro decision processes? Ready to go on? Yeah, the Bellman equation was the solution to the Markup decision process. Yeah. Okay, so if I say Bellman equation, everyone's good? All right. Okay, good. All right. So now let's change this around, right? And we're going to now talk about meta-level Markup decision processes. So a meta-level Markup decision process, the state, instead of being a physical state of the world, is a belief state, right? And the action, instead of being an action in that world, is a computation that we're going to perform. And so now the idea is that you're in some belief state, you're going to perform some computation, and what that computation is going to do is give you some information which you use to update your beliefs. And the dynamics here, rather than being the dynamics of a physical environment that you're in, are now the dynamics that are associated with, say, Bayesian updating based on the information that you obtained by executing that computation. And then that computation is associated with some computational cost. At some point, we sort of iterated through a sequence of beliefs, and we get to the point where we have a final set of beliefs, and we say, you know what, now I'm ready to take this action. We have a special action that says, take the current beliefs that I have and take the action in the world, which is the utility maximizing action with respect to the current beliefs that I've acquired. And this is called a meta-level Markup decision process. And so now the key idea is that having formulated our meta-level problem in these terms, we can use those same methods that we use for finding an optimal policy, right, Bellman equation, right, to give us a characterization of what the optimal meta-level policy looks like. And that optimal meta-level policy is our cognitive strategy, right? Because it tells us, based on the beliefs you have, do this, think about this, do this, think about this, think about this, think about this, and now I'm done thinking, right, and I'm ready to take an action in the world. And so this is the framework that we're going to use for then deriving what optimal cognitive strategies look like in a bunch of different kinds of decision problems. Make sense? I'm going to give you some concrete examples in a moment, so try this out. Okay. So I'm going to run through an example which is multi-alternative risky choice. This is work with Paul Kruger, Fred Callaway, Triangle, and Falk Leader. Multi-alternative risky choice is a fun sort of case to look at this in, because it's a case which has been extensively used to try and identify the kinds of cognitive strategies people use in decision making. So the way that this is set up, I'm using this what's called the mouse lab paradigm, where we give people a bunch of choices between gambles. They have information about the probabilities that are associated with different outcomes, here represented by balls in an urn, so they have information about how many balls of different kinds appear in an urn. What they don't have information about is the payoff that's associated with those gambles. And so what we're doing is basically externalizing the sort of information gathering process that you might engage in when you're trying to make a decision by making it so that the information about what the payoffs are is not immediately available to you, and you have to make some meta-level decisions about what information you gather before you then go on and make a decision. And so the way that you gather that information is you click on one of these cells, and then when you click on that cell, it then reveals what the payoff is that's associated with that outcome for that gamble.
What's on the left ball, 29A?
This is the probabilities associated with the outcomes. So there's like, say, 4 outcomes, A, B, C, and D, represented by 100 balls that are in an urn, and there's 29 balls that have an A on them, 39 that have a B on them, and so on. So this kind of paradigm has been used to explore cognitive strategies that people use for making decisions. Classic strategies include things like take the best, right, where you say focus on the outcome that has the highest probability, gather information about the payoffs associated with that outcome under the different gambles, and then choose the gamble that has the highest payoff for that highest probability outcome. But we can, using this kind of setup, actually derive what the optimal cognitive strategy looks like by formulating this as a meta-level Markup decision process. So in this case, the beliefs you have are about the values that are hidden behind those gray cells. The computations you're performing are basically evaluating those cells. There's some cost associated with those computations. And then at the end of the day, you decide, I've got enough information, I'm ready to act, and you get a payoff which is associated with the gamble that you actually ended up selecting. Okay? So as I said, in doing this, we're externalizing that metacognitive process, right? Because we can actually follow the clicks that people are making to gather the information and so on. And so that's how I'm going to look at this. And then I'll show you another experiment where we don't externalize the computations. But this is a good sort of warm-up for looking at strategies that we get. So to look at this, what we did was actually just generate all of the mouse lab tasks. And tomorrow I'll talk more about running these crazy giant experiments, but that's essentially what we're going to do in a moment, where we can manipulate the stakes that are involved in these gambles, the dispersion of the probabilities that are involved, and the cost of gathering information. And so we just, in this case, had 2 distributions of payoffs. Dispersion was manipulated by generating probabilities from Dirichlet distributions with different parameters. So this goes from one which is very sparse to one which is very uniform. And then different levels of the cost involved for clicking that are now sort of increasing exponentially. And then this gives us 2 payoff conditions times 5, dispersion conditions times 5, cost conditions. So that's a total of 50 conditions. In each of those 50 conditions, we generated 20 scenarios, and then found the optimal cognitive strategy in each of those scenarios as a way of looking at what these optimal strategies look like. And yeah.
So the scenario, what are scenarios?
So this would be a scenario, right? So it would be, we specify a payoff distribution. We generate probabilities from this distribution, and then we have some specified cost, and then this is realized into a matrix where the payoffs now appear within this matrix. You just don't know what they are. Okay? And so now the idea is that as you click on something, you get some information, and so we have 20 different configurations of those numbers in that matrix for each of those 50 different conditions. So it's just a realization of the stochastic process that generates the stimulus. Yeah. Okay.
So you have 20 different realizations, but then you optimize numerically, or?
So we generate the, so we generate.
On those 20, so you'll have some variance.
So we generate the optimal strategy. So the optimal strategy just depends on these things, these distributions, right, and costs. So we can work out what the optimal strategy is conditioned on this information, and then we can look at what that looks like when we put it in those 20 different scenarios. Yeah. And so the way I'm going to represent this, so this is, say, what the output of the algorithm is, right? So it sort of clicks on a bunch of these cells, reveals that information, and then decides it's got enough information to make a decision. So I'm going to represent this by reordering, so we sort of need to canonicalize this to compare across different scenarios, right? So I'm going to canonicalize this by ordering the columns by the number of cells that are revealed in the column. So we have column number 1 is the most cells revealed, and then so on. And then reordering the rows so that they are ordered by the sequence of clicks. So whichever row was clicked on first, then the next one, then the next one, the next one. Sorry, no, I did the wrong way around, sorry. So the rows are ordered by the number of clicks across the row, the columns by the sequence of clicks. Okay. So what that does is take our original click layout and then translate it into this canonical ordering. And then we can then look at all of the responses that we get from the optimal strategies across all of those different scenarios and look at what kinds of regularities that we see. And the way that we do that is by performing k-means clustering on these matrices that characterize the strategy. Yeah.
So all the plays have depth 8 here?
All of
so
the...
It's an optimal strategy for an horizon at 8? Or?
No, so they could potentially reveal all of the cells in the matrix. So it's an optimal strategy. So the limiting horizon is revealing all of the cells. Yeah.
But the optimal strategy that you calculate, which I guess you calculate numerically, includes the optimal time, or you do an optimal strategy for a given bit?
So the strategy has in it this termination decision, right? So what it's going to do is at some point say, I've gathered enough information, and I'm going to stop.
And that's guaranteed to be before 20?
No, I'll show you, like in some cases it's optimal to just keep on going. Yeah. So we do k-means clustering on these strategy executions, and then that's what this looks like, right? And so this is the average of the strategy matrices that come out of the k-means clustering, where I'm showing the probability with which you would click on a particular cell, and so with yellow being more clicks. So a couple of these are things that are sort of familiar classic strategies, right? So this strategy says, click on all the cells, right? So this is the one that says, gather all of the information and only act when you've got all of the information.
So these 4 are 4 clusters of strategies.
Yeah.
And you chose, you did k-means for different k's, and then you took the best one according to...
Yeah, so basically what we see if we continue this is we just see repetitions of the same strategies. So these were the ones that were discrete. Yeah. And then this strategy here is the take the best strategy that I talked about, where you focus on the row that has the highest probability, and then you click all the way across that row. And so what we're able to do then is just sort of rediscover that these sort of classic strategies are things that make sense to perform in this task. But we also find some new strategies that actually correspond to things that people had not previously observed in this literature. So this first strategy here is a kind of satisficing strategy. So it's one that says, click a few times on the highest probability row, and then but you don't need to observe all of them. You just do a few of these, and then you make a decision on that basis. And then this one, which is a hybrid of that take the best strategy and a satisficing strategy. So what that looks like is something like this, where you click across a few times. This is the one I showed you, where you click across a few times, and then you make a decision. And so this is a strategy that makes sense if you're in a problem where there's not a lot of dispersion in these underlying probabilities, and the stakes are not particularly high. It's not worth doing a lot of cognitive investment, and so as a consequence you gather a little bit of information and you take an appropriate action. So these are the kinds of strategies that we find in the optimal solutions that come from solving that meta-level Markup decision process. A natural question we could ask is, what do people do? And so the crazy experiment we ran was we took those 1,000 scenarios, and then we had like 2,400 people online do all of those scenarios. So we gather multiple observations for every single one of those scenarios. And then we end up with the same kind of strategy matrices produced by people that we were getting from our models. And we can ask what the patterns are that show up in those strategy matrices. Yeah.
So I thought the model was the experiment, but the model is what distinguishes the different why don't you have a single
strategy
Yeah.
because of this variability in, we go back here. So,
in different conditions, you
Mhm.
have different strategies?
yeah, so as you vary the payoffs and dispersion probabilities and costs, that's going to select for different strategies. And I'll show you in a moment what that looks like. Yeah. Yeah.
So in this strategy, the third one, it's not just which boxes get covered matters maybe, but in which order.
Yeah.
You also pay attention to the order in which people click, or?
Yeah. So here we're ordering columns just by which one they click on first, right?
But in 10.3, then do you explore the first row and then stop doing
Yeah,
columns?
so
or
the
first
rows are ordered by, sorry, I think I said this wrong before, they're ordered by the probabilities that are associated with the payoffs, right?
Yes.
So this is, people definitely look at the highest payoff, probability payoff, and then they look at most of the next highest probability, and then some of the next one, and some of the next one.
In that
Yeah.
order.
Okay, and so if we do the same kind of analysis on the human data, this is what it looks like, right? So again, just running k-means analysis, and what we find is basically the same for strategies are the things that show up in the human data as well, plus one other strategy. This is the strategy where you don't gather any information, you just choose a gamble, right? So people sort of acting completely at random. That's not something the model ever does under these conditions, and I'll talk a little more about that in a moment. Yeah.
I may have misunderstood you, but the model results depend on the parameters.
The model has information about the payoff distribution, the probabilities that are associated with the outcomes, and the cost.
And same for the participants?
Yep. And they, participants were always in one payoff condition and then, and one cost condition. And then they saw scenarios that varied in the probabilities that appeared.
So they learn these parameters from experience?
Yeah, that's right.
Unlike.
And for a given condition, does a participant switch between strategies or a given participant?
Yeah, and they should, right? So if the payoff probabilities are different
No, for
between
a
two
given
products.
condition.
Oh, so that we only get one realization per participant per.
I see. So you don't know if the variation is within subjects or
Yeah. Okay. So I just told you, okay, these are the kinds of strategies that you see. The other relevant question is, do you see those strategies under the same circumstances? And the answer is, to some extent, yes, right? So this is showing, just as we vary the stakes, the dispersion of the probabilities, and the cost, how the choice of these different strategies varies. So if we look at the model here, I think the easiest one to understand is cost, right? So if the cost is 0, then the model says evaluate all of the cells, right, and just calculate expected utility, and that's the optimal strategy. Makes sense. As the cost increases, then you see some of these more conservative strategies show up, right? So this is the one which, the blue is the one that searches one entire row and then searches a little bit of the next row. And so that's the next most popular strategy by the model. And then as the cost increases even more, then you see the less exploratory strategy, the one that just searches a few entries of that row, being the one that starts to dominate, right? And we see the same kind of profile in people, where you see more red, that's exploring all the cells when the cost is 0. You see an increase in the use of the orange strategy. You see blue being sort of the most popular strategy overall. But you see less sensitivity to this than is demonstrated by the model. There's a couple things going on here, right? So one of these is that this is just the cost that we're giving people. It doesn't take into account any of the intrinsic cost that people have just sitting in our experiment and not doing something else. And so we ran a subsequent experiment where we just forced people to engage with the same decision problem for a fixed amount of time, regardless of what strategy they executed. And then that produced more of this kind of behavior. But I think the sort of overall idea here is that we can measure the kinds of strategies people are using. They're somewhat adaptive, but they're not as adaptive as the model says that they should be. And so one thing that we can actually do is we can actually sort of say, how well are people doing here compared to that, sort of optimal resource rational standard? And you can see people are achieving about 60 to 70% of what they should be achieving, right? So this is, again, varying these different aspects of the task. This is the performance of the model here normalized across tasks, because different tasks have different payoffs, and then people. And so they're sort of doing fairly well, but they're not doing as well as they could. And then the other thing that we can do using this kind of model is to go in and actually analyze why it is that they're not doing as well as they could. We can sort of break this down. We can say, this is when they're getting it right. They're getting it right some proportion of the time. But we can also look at, for example, how much of the results can we explain in terms of the implicit costs of information gathering by making a variant of the model where we have a free parameter that we estimate that tries to estimate that cost, and then seeing how much better we do in terms of accounting for the strategies that people use. Or looking at imperfect information use, where we assume that people have some probability with which they miss a piece of information and don't incorporate it, and so we get a model that has a free parameter that incorporates that, and so we can sort of add all of these things in. And when we do that, we find that the biggest factor that's contributing to people's errors is basically just not using the right strategy for a particular problem. And so that gives us a sense of where it is that people are going awry in solving this problem with respect to, I think, a more sort of reasonable standard of normativity for solving this kind of decision problem. Yeah.
In a given condition, how similar different participants are? I mean, the model would predict that they should be identical, right?
So it's hard to say that, right? So the model predicts that the policy should be the same, but because if you make that initial choice, you get a different number depending on what you click on, right? So you can make your first click actually. So that's, yeah. So we could look at that, right? So we could look at whether we see greater variability than the model predicts in terms of the strategies for a specific realization. And I think we would see that, right? The other, this big chunk here, this is that random strategy that I was talking about, right? So there's a large proportion of the mistakes that people are making are cases where we just have participants that are not motivated to perform the task and are just they're just gambling without gathering any information. And so that's an extra source of variability.
How should I interpret this, or what should I learn from this? Is it that people are not optimizing and doing some kind of self-optimization, or is it that the normative prescription should be refined?
So I would look at this, right, which is telling you that most of the time people are doing the thing that the model says is the optimal strategy for that problem. And then I would look at this and say, the rest of the time they're not using the appropriate strategy for that problem, but they're still using a strategy that's a reasonable strategy for solving this kind of problem, right? So like if we go back to this picture, right, like the things that people are doing when they're not doing that are mostly sensible things. It's just that they kind of used that in a situation where they should have been using a different strategy for that problem. So you can think about them as having a good set of heuristics for solving these problems, but then occasionally making mistakes in which heuristic they're deploying, which I think is a different picture from the one that says people are doing something that doesn't make sense, they should be doing something else.
But it's also a different picture from saying people
Yeah.
are doing optimal,
That's right.
but not doing it
That's
very
right.
well.
That's right. And but I think it's actually the more informative picture, right? Because it's the one that tells us if you wanted to make people better at solving this problem, rather than telling them you're doing it wrong, this is not the right way to think about this, you can say you've got the right, you basically want to train people to recognize when a particular strategy is the right one to use for a given problem.
And you have some idea why they suddenly switch from one strategy to another?
Like why they're using the wrong strategies in
Yeah.
the situation? No, we don't know that. That's a good question. Yeah.
But if I understand correctly, you're looking at a problem where there's a cost for acquiring information.
Mhm.
You're looking at the optimal strategy,
Yeah.
and you're seeing how people are doing.
Yeah.
How's that related to cognitive costs?
So I said
You're
we've.
simply checking
Yep.
whether people use it, and you have interesting results about
Yep.
that, but I don't see how it's related to cognitive costs.
No, so I said in this experiment we're externalizing the costs, right? So and externalizing the clicks because we're measuring them. I'll now show you a case where we're not doing that. Okay. So what I'm going to show you now is how we can use essentially the same model to make sense of a very different kind of decision problem, right? And so now this is a decision problem that's called simple choice. So this is joint work with Fred Callaway and Antonio Rangel. So the idea is I present you with 3 different snack foods, and you're going to make a decision which one you want. While you're making that decision, I'm going to keep track of what you're looking at, right? And so it turns out that when people do this, there are some very robust results about what happens. So basically, people spend more time looking at the items that they consider more attractive. And that happens increasingly over the course of the decision process, such that they're more likely to be looking at the thing that they end up choosing at the point where they end up choosing. And so these kinds of phenomena have previously been explained using models like the attentional drift diffusion model. So this is a variant of a standard drift diffusion model where you're sort of drifting, you have a signal which is drifting as you're accumulating information, but the rate at which you're accumulating information varies depending on what you're looking at. So if you're looking at the object on the left, you're accumulating information at a higher rate for the thing on the left. If you're looking at the object on the right, you're accumulating information at a higher rate for the object on the right, and then eventually you get to a decision point. But this kind of model doesn't explain how it is that you make the decision of what to look at in the first place. And so what we were interested in was using that same kind of framework that I just showed you to then talk about how it is that people might select which things they're thinking about in the context of trying to make these kinds of simple choices. And the setup is very similar to the one that I showed you before. The idea here is that you have these different options, each of which is associated with some utility. You don't have direct access to those utilities. Rather, you have some prior probability distribution, which is your prior distribution over the utilities you might associate with these things, which you're updating by looking at that thing, thinking about it, and then getting a sample, which comes from the true distribution of utility you associate with that item, that you then use to update your estimate of belief, right? So in the previous model, we assume that you get all of the information when you click on a cell. It tells you exactly what the payoff information is. Here we're assuming you just get a sample from the distribution, and you make an update based on that sample. And so now it can make sense to spend more time looking at this thing in order to get a higher precision estimate of the utility that you associated with that item. So with that minor tweak, we can do the same thing. We can set up what the optimal cognitive strategy looks like, right? So now our belief states are these utility distributions that we have associated with different items. Again, our computations are looking at a thing, thinking about it, evaluating it. There's a cost to spending time doing that. And in this model, there's also a cost for switching your gaze from one thing to another. So you have an additional switch cost. And then the idea is that at some point, you've got enough information about utilities, you make a decision, and that decision you're going to then get a payoff that's associated with the item that you choose. And so we evaluated this model on a few different data sets. I'm just going to show you one of them. This is from an experiment that was done by Krobich and Rangel. So in this experiment, they had people come into the lab. They came in hungry, so they had to fast for 3 hours beforehand. They saw a bunch of these snack foods. They rated how much they liked those snack foods. And then they went into a phase where they would look at this dot, they'd see 3 snack foods, and have to choose which of these snack foods they liked, while their eye gaze was being tracked in the course of this experiment. And then at the end, in order for incentive compatibility, they had to stay in the lab for 30 minutes, and they could only eat the food that they had chosen in one of these trials at random. Okay, so what we can then do is look at the data which comes from this experiment and compare it to the predictions from our model. And so here I'm just plotting, this is the probability of choosing an item versus the amount of time spent looking at that item. The black line is the human data, and this is just showing what I told you before, that people spend more time looking at things which they end up choosing. But you can see that the red line here, this same relationship falls out of the model that I was talking about. And the reason why this comes out of the model is basically, if you imagine a situation where you have these items, you're trying to figure out which ones you want to eat. You might look at each of the items, you get some initial estimate, you get a sample from each of them, some initial estimate of the utility you associate with that item, and then it makes sense for you to focus your attention on those items that you got a higher estimate for, right? You can sort of start ruling things out. And so that means that you're going to be spending more time looking at higher utility items because the information about those is more relevant to the decision that you're ultimately going to end up making. Consistent with this, you also see that high-value items are fixated more by the humans and by the model, right? So the model is going to spend more time looking at those things that have high value because, again, it's trying to figure out which is the thing which is best, and you want to allocate your samples between those things that look best. And that this happens particularly as time goes on, as you start to rule things out and you start to converge on the things which are going to be the things you ultimately choose. Yep.
Yeah, so I think this optimal strategy makes sense when you have 3 items or more than 2, but we observe the same thing when there's only 2 items. So
yeah, so this is a good question, right? I said we evaluate on a few different data sets. We also look at a 2-item data set. So intuitively, the issue with 2 items, right, is that gathering information about one item also gives you information about the other in some sense, because what you care about is the difference between those items. And so sampling either of those gives you information about that difference. The way that we model the two-item data is by assuming that that initial distribution that you start from is one which is actually a prior distribution that's below the values of the items that you observe. And then it gives you a dynamic which ends up looking a lot like the drift diffusion dynamic, where you are updating your estimates, and so you end up sort of updating towards the item values, but you're gathering, you can be gathering different amounts of information by looking at different items, and I can show you in our paper how that works.
Yes. So that assumes that like your brain has some immediate estimate of the values.
Yeah.
And
Yeah.
okay, so this like use.
Yeah. So it assumes you start off from a biased starting point, and you need to update away from that. Yeah.
And this all survives if you remove the last fixation.
Yeah.
It doesn't depend strongly
No.
on that.
Yeah.
Can you remind you what the model is?
Yeah, so it's just this model that says you are, when you look at an item, you generate a sample from that's centered around the true utility associated with that item, right? And that's it. Yeah, and then you have a cost for looking more, and you have a cost for switching.
Is it important to have this cost of switching?
It's a good question. So I think it makes our model fit better, but it's not necessary to get the qualitative results there.
Two items, if you don't have switching cost, you'll be going back and forth.
Yeah, that's right. That's right.
So
Yeah.
two items, it doesn't matter.
Yeah. Okay. All right. So when I started out, I sort of like talked about things like chess. I'm not going to get to chess today. I'll actually talk more about chess tomorrow. But I can talk about something which is like one step closer to chess, right? So far we've been focused on these simple decision problems. We've also looked at the same kind of behavior in the context of planning. So now the planning problem is you have this spider that you're trying to help navigate through this maze, right? So it's a multi-step planning problem. You have to try and figure out which of these paths is the path that's going to yield the greatest reward. But like our mouse lab task, you don't have information about what the rewards are, and so you need to evaluate these options in order to figure out how to help the spider navigate the maze. And the way that that's set up ends up being very similar to the way that we set up the mouse lab problem, right? So you have beliefs that are about what's behind those cells, you have costs that are associated with gathering information, and you get some reward based on the path that you end up selecting. But what we can look at here is which cells people choose to gather information about when they're trying to engage in this planning problem. And we can compare the optimal solution to this kind of meta-level MDP to the kinds of behavior that people produce and the kinds of algorithms that are used in computer science. And so these computer science algorithms turn out to work less well than the optimal algorithm for fitting the human data. I'm not going to spend a lot of time on this. I just want to sort of give you an intuition for it. The reason why is that people display a kind of adaptivity in their planning, which is not something which is displayed by those canonical computer science algorithms. And that's reflected in these data. So this is when we look across these problems and look at two dimensions. One is how many clicks people have made so far, so how much they've explored the payoffs in that graph, versus this is the best expected path value they've discovered so far. And then the cells here are colored by the probability that people stop searching. And what you can see here is a similar kind of sort of satisficing behavior from the behavior that we saw in the other choice problems, where as you move from the bottom left here to the top right, people are more likely to stop searching, right? Based on as the expected path value increases and the number of clicks that have been made increase. And so what this reflects is that people are sort of sensitive to the fact that they've already explored a bunch of the graph, they've already found a pretty good solution, they're willing to stop searching because they've got a pretty good solution so far.
Didn't they expect that?
So this is because they don't know what's behind some of the cells, then they have to be computing an expectation over what value could be behind that cell. Right, so this is based on, it's based with respect to the beliefs they have about the possible values that could be there. So in the actual experiment, there's only 4 possible values -5, oh, it's 5 values. -10, 5, 0, 5, or 10. And so,
Uniform?
yeah,
So with respect to uniform.
yeah. So then in that case, there's a uniform. So this kind of adaptivity that we see in people, we see in this optimal strategy for solving this problem, and it's not shown in the sort of standard computer science algorithms for planning. And so this gives us a way of sort of showing that people are, when they're engaging in this kind of planning problem, doing so where they're making sort of efficient use of their cognitive resources in a way that's not canonical, at least for the way that people think in computer science are solving these planning problems. So I'll come back. This again was an externalized experiment, right, where people are clicking on things. Tomorrow I'll talk about the non-externalized version of this.
The difference between optimal and first best.
So optimal is the thing that's derived from solving our meta level MDP. Best first is a standard planning algorithm that's used in computer science. So it's basically using a heuristic to calculate a value that's associated with the different cells, and then choosing which cell to explore based on that heuristic.
Why is there a difference between the optimal and first best?
Because this is not an optimal algorithm for solving the problem. It's just it's a way of doing planning.
It's just a way.
Yeah.
Okay.
Yeah.
But I guess why did they pick that way?
Because this is like if you read a computer science book about how to solve a planning problem, it'll tell you to use this algorithm.
So this is an algorithm that works well in a more general class of problems?
Yeah.
Okay.
So, I guess the adaptation to the evidence for resource rationality.
Mhm.
Do you have a condition where you provide
That's a good question. We haven't done that. But Falk has done a lot of follow-up work on these planning problems, including using tutors, and so he might have done something like this. Okay. So the last thing I wanted to talk about was making this connection back to representation, to talk about some of the things that Mike has talked about before. And again, I think you can use the example of chess to motivate this, right? So I said Kasparov here is searching fewer positions, but he's not just doing that. He also has a representation of the chessboard which is different from the representation that the computer has. And so, this is from some data that were collected looking at actual chess masters, where you would show them a chessboard and you could look at what their sequence of eye movements were and what pieces they seem to be encoding. And so the representation that the chess master has is one where certain pieces are sort of emphasized, other pieces are de-emphasized based on the relationships that they have and the importance that they have in that position. And so what we're interested in is understanding how it is that we can think about people developing these kinds of simplified representations for solving different kinds of planning problems. And this is joint work with Markup. And so we used something a little simpler than chess in this case, which is a simple kind of navigation problem, where people are given this navigation problem where they have to start in a particular position, get to a particular position, and in order to get there, they're going to have to navigate around some obstacles. You can see a path here that they execute. And then after they do this, we would ask them a question like, how aware were you of this obstacle? Or we had a few different variants on this. We also did things like show them an obstacle in different orientations and ask them which orientation the obstacle was in the problem that they were solving. And so people, when they do this, do a good job of solving this problem, right? So they can, sort of find good paths through these simple mazes. And from them, we get sort of meaningful differences in the awareness that they report for the different objects that appear in these arrays. So for example, here the shadedness of an object represents how aware people were of it. And as I said in other versions of this experiment, we've done sort of analogous things where we look at how aware they were of the orientation of that object. So if you look at these examples, what you can see is that people are representing a simplified version of the scene. It's one where some of these more peripheral objects are not really things that they think about at all. They're more focused on the objects which are sort of related to the path that they end up following. And we can formalize this by thinking about their planning problem not just in terms of a sort of standard planning procedure where you're trying to derive a policy in the context of a task, but in terms of one where you're formulating a construal of that task and then planning within that simpler version of the task. And so what you're doing is starting with this navigation problem, constructing a simplified representation, and then using that simplified representation to construct your plan. And so in order to think about this, we can define something which is analogous to the value of computation that I talked about in those previous examples, where it's like how worthwhile it is to execute a computation. You can also ask how worthwhile is it to have a particular representation. And we can assign a value to a representation based on the utility that you derive from having that representation, so the quality of the plans that you can construct using that representation, minus a cognitive cost, which is the complexity of constructing that representation. The way that we construct this construal is in terms of a model of the world, which is expressed as a sort of multiplicative set of, where the transition probabilities are expressed as a multiplicative function of individual objects that you could represent. And so this captures the fact that, you can't transition through different kinds of objects. And so the way that we formulate this problem in our case is you're trying to construct a construal which corresponds to a subset of the objects you're going to represent, and then the cost of representing those objects increases with the number of objects that you end up representing. And so with this formulation, we can then optimize the construal, the extent to which you're willing to represent different objects in terms of this trade-off between how well you can plan in an environment that just has those objects in it versus the extra cognitive cost of representing the full set of objects. And when we do that, we get out of the model predictions that look like this. So this is starting point, goal, and then the construal of the objects. So these are the objects that are that the model says you should think about in the context of solving these planning problems. And then we can compare those against the human data, and we actually get a remarkably good correspondence between people's awareness of these different objects and when they're solving these problems, and the predictions that come out of this simple kind of construal model.
Sorry, how do you measure awareness? Do they have to click or?
Yeah, so it turns out you can just ask people how aware were you of this object, and it predicts a lot of other things. But we were skeptical of that, and so we did it in a bunch of different ways. So we would show them the object, but we would rotate it or show it in a slightly different location, and we'd show them two things, where one was the correct one and one was a variant, and we'd look at the rate at which they could detect which was the correct one. We also did versions of the experiment where we put a dot on objects, and then we'd say, which object had the dot and things like that. And it turns out all of them correlate with just asking people to rate how aware they are of whether the object is present. Yeah.
So the colors here are the probabilities of being aware of.
Yeah, it's the reported probabilities of representing that object.
And why is the model probabilistic?
The model is not probabilistic. So the model actually says yes or no. At least this version of the model. We subsequently developed a more sophisticated model that outputs more continuous probabilities, but the version I told you about is just one that says represent the object or not.
What's special about the cross at the center?
That's conserved across all of our mazes. So that's kind of like, that's to orient people in all the mazes. They see the cross and then they see the objects. No questions?
If it's a yes or no model, then why is it shaded gray? Like, why is there a small probability?
It's just to show you that the object is not represented. So you can see the object. So, I mean, the reason I want to talk about this is that I think you can think about this as being related to some of the things Mike's been talking about, right? About efficient coding, right? You can think about this as a kind of efficient coding in a way that's task-oriented, right? Very much in lines with the stuff that Mike was talking about at the end of his talk, where it's telling you how to represent the scene in order to be able to plan effectively within that scene. Okay, so I'm going to wrap up. So I think resource rationality gives us a better normative criterion for evaluating human behavior in these kinds of settings, right? It's one that's a realistic standard that we could expect an agent with finite computational resources to achieve. And it gives us a more realistic sense of when, more classical rationality is not achievable. As you saw, it's not a standard that people always achieve in the context of the experiments that we were presenting. But in those cases where people don't achieve it, it also suggests a different way of addressing deviations from that normative standard, right? So the kinds of interventions it suggests are not one of telling people that they're wrong and here's how you should be solving this problem, but rather trying to understand what kinds of strategies are cognitively available to people and helping them find better strategies that they can use in solving that particular task. I'm not going to have time to go through this, but we've done a bunch of work using this framework to formalize nudging. So basically the idea is that if we've got a model that tells us what cognitive strategy people will adopt based on the information that's available to them, we can use that to construct environments that support better decision making in people. So you can kind of think about this as, if part of the problem is we don't have enough computational resources, we can offload those computational resources and put them in the environment and pre-compute environments that make it easier for people to make decisions using the limited resources that they have. And so using this kind of approach, we can actually come up with sort of optimal nudges that lead people to make better decisions. And I think sort of finally, by emphasizing cognitive processes and things like Markup decision processes, it also has the benefit of supporting the search for the mechanisms that might underlie decision making. So again, that sort of classical expected utility gives us a few things that we can look for in the brain in terms of like things that you need to represent in order to make those decisions. But this kind of framework gives us a much wider set of predictions about what it is that should be going on inside people's heads. It tells us what optimal cognitive processes look like, not just what optimal behavior looks like. And I think that's something that, to me as a psychologist, is exciting. And it also makes a connection to the literature on reinforcement learning, where a lot of work has been done trying to identify the kinds of mechanisms that can support solving these sorts of sequential decision problems like formulated using Markup decision processes. Okay, so thank you. We have a couple of minutes for questions if people have any.
Well, I might have missed something, but what I gathered from what you showed us is that people have a set of strategies, which is actually quite good in the sense that they are optimal in certain situations.
Yeah.
And the main mistake that's being done is that they apply a certain strategy that is optimal in one context to a context where another is optimal.
Yeah.
Actually, from what you showed us, it seems that people are doing a lot of it.
Mm-hmm.
But what I don't quite see is how you connect this to how you derive this as a result of optimal use of cognitive resources. I don't see the connection between the two.
So, I mean, so in that particular experiment, right, in the mouse lab experiment, or I think the simple, I'll show some more data tomorrow that engage with this for something like the chess case, but I think the simple choice experiment is the one which is the most naturalistic experiment, where it really is about just what are people, the limited resources they have is attention and capacity to think about these. The food, yeah, that's right. So I agree with you, because in the other experiments what we were doing was externalizing the actions and the costs that were associated with them, right? And then using that as a way of validating the framework. So the simple choice experiment, I think, is the best illustration of it actually being an internalized cognitive cost. And then tomorrow I'll show you some data for chess that I think is the analog for the planning problem that I talked about. Yeah.
I'm showed the experiments. The dry experiments of navigating in the city or crossing areas, and the people tend to turn more into the point than to make a more simple way to cross around.
Yeah.
And this is an experiment that you showed. This is different because it's more simple context that I think, or it's to make more complex context for your experiment in lab. Will be the same, or it's just because it's small, not.
So that's a good question. So I think part of that is that in our task you have a two-dimensional bird's eye view, right? And so if you run this in a three-dimensional setting, the reason why we didn't do this is that it takes a lot of training with a new environment to get people to the point where they can navigate in a new environment, right? But I think if you did this in that kind of environment, then you'd be more likely to see that.
Yeah, and with VR,
Yeah.
right?
Yeah.
But it's not complex, right?
Hmm?
It's not so complex to organize.
Yeah, that's right. I think that'd be a good thing to do. Yeah.
Two questions, one about cost, one about benefit. So benefit, so across different studies you've done with us, sometimes the objective function is to minimize variance, sometimes the objective is to maximize expected reward. Does it matter? Second,
Yeah.
regarding cost.
Oh, can I just answer them one at a time? So for the first one, the reason why we cared about minimizing variance was to maximize reward. So in the paper we show that that relationship holds, but it wasn't. It's not that we extrinsically set out to minimize variance. It's that that's the thing that for small samples maximizes reward. Yeah.
Second question on cost. Is it also connected to the entropy-based information concept?
So this is part of, I think, I sort of had this picture at the start, right, of what this space looks like. So in rational intention, right, so you have this information theoretic cost versus, in the models I've been presenting, cost is expressed in terms of time and computation. So the place where, as I said, you could think about them maybe converging is something like sampling, right? So if you think about, I am going to generate some number of samples from a signal, right? So I have this thing that I want to measure in the world, and the standard, like rational intention version of this, you just have a knob that you can turn, which is the fidelity with which you measure that thing, but there's a information theoretic cost that's associated with it. My version of that would be, you can choose how many samples you want to generate from that thing, right? And there's some computational cost that's associated with how many samples you generate. And there are going to be cases where those two things converge, right? Where the information theoretic cost, based on increasing fidelity for just adjusting that signal, and the time cost of the number of samples you need in order to get a certain fidelity are going to line up. But I think that's a way that you could make that connection if you wanted to.
That's not always.
Sorry?
The equivalent is not always the case.
No, that's right. Yeah, last question, I think.
So in the metacognitive model, the movement was happening in this belief space, and the transition dynamics was being given by some inductive Bayes rule.
Yeah.
Okay. And this Bayes rule was being applied on distributions which were already specified, which were representative of the true distributions in the system. So for instance, the uniform distribution, all of these things are already given to the cognitive agent. Okay. One way to kind of explain the part of humans that are not really
as being wrong about what those distributions are.
Some slight amount of misspecification.
Yeah.
I mean, is there
Yeah,
something?
no, I think so from my picture here, right, of what the sources of error are, I think that's part of it, right, which is that the model always knows what the distributions are that are these, arrays are being drawn from, and people have some noisy estimate of that. And so, yeah, I think that is a good thing. Okay, thank you. I'll be back tomorrow.